Welcome back to the YouTube channel. This is a continuation of the video I started on work done. And in my first video, if you have not seen that, I want you to go back and check my channel for the first video on the introduction to work done. Now I continue with that, looking at work done against the force of friction. Or force of friction can also do work. We can have work done by friction and work done against the force of friction. And when work is done against the force of friction, energy is lost. And that's why we have in machines, the manufacturer and the users, they try as much as possible to minimize frictional force by lubricating the moving parts of the machine. So the more the frictional force, the more the energy that is lost in the process of making use of that machine. So like I have a case where there's a box of mass lying on this horizontal surface and a force P, I call that the applied force, is about to move this block or this box through a distance d. But that force is being opposed, that motion, that movement is being opposed by the force of friction, Fr. Now we can write expression for the work done against the force of friction because this applied force will be such that it overcomes the force of friction. That is, if this block must move with a constant speed, then the applied force P must be equal to the frictional force. So that's the minimum force that must be required. So the work done against friction, if the body moves with a constant speed, along this horizontal surface, then the work done by friction or against the force of friction is force P multiplied by distance d. So I can say work done against friction F or W equals to P times d. Or we can say Fr, which is the frictional force, multiplied by distance d. Okay, but sometimes the force P is made greater than the frictional force. So that in this case, the block actually accelerates while it moves through distance d. So in that case, we need to find the total work done, also find the useful work done, and also the work done against the force of friction. So, but work done against the force of friction or by frictional force is this frictional force times distance moved. And in that case, where force P is greater than Fr, it means that the work done is going to be work done against frictional force. It's going to be frictional force multiplied by the distance moved against the direction of the friction, because actually this block moved this way and frictional force is acting this way. So the direction, the distance is in opposite direction to the direction of the frictional force, as you can see there. So we have frictional force and distance moved in a direction opposite to the direction of the frictional force. Now I have an example here I want us to look at together. We have a box of mass 5 kg lies on a rough horizontal surface. An applied force of 10 Newton moved it a distance of 5 meters against a resistive force, look at that, of 6 Newton. The question says calculate for this box of mass 5 kg the useful work done. Now what I need to tell you here is that the mass of the block is not part of the solution to this question because the distance, the formula given before, has nothing to do with the mass of the block. And even the weight of the block as a result of the mass does not act in the direction of motion. We are looking at a body that moves along the horizontal surface. So the mass of a block or its weight acts vertically downwards. So since the motion is not in this direction, it's actually along this line, it means that the weight has no work done in this situation. Okay, so calculate the useful work done. When we ask to find the useful work done, we are talking about the minimum work that will be required to move this box of mass through this distance, 5 meters, assuming there were no frictional force. So when the question says useful work done, we are looking at a case where frictional force is negligible. There's no friction acting between the two surfaces, that is the surface of the block and the horizontal surface. So the minimum work done is going to be the applied force multiplied by the distance moved in the direction of the force. That will give me 10 times 5. That gives me 50 joule. That is the minimum work done. All right, but here it's not actually 10 times 5. because you can see here that this 10 Newton is the applied force. So we're actually going to find the difference between the applied force and the resistive force. So the minimum work done actually, let me call that WM, is 10, sorry, it's a 4 multiplied by 5. That is 20 joule. How did I get before again? Because I subtracted 6 from 10. This 50 joule I calculated is for the total work done. You see, the total work done by the applied force, let me call that WT, is equal to 10 times 5. That gives me 50 joule. But the useful work done is the difference between, that is the force, which is the difference between 10 and 6, and the distance moved. The work done against frictional force can simply be the difference between the 50 joule, which is total work done, and the minimum work done. So the work done against friction, I can call that WF. That gives me 50 minus 20. That gives me 30 joule. This is the work done against the force of friction. Or I can even calculate it by using frictional force, which is 615 times distance moved against the direction of friction, which is 5. But the distance is still the same, 5 meters, and that gives me the same 30 joule. So you can see that now what can be done in this situation where you are given two forces. One of them is the applied force, and the second is the frictional force. Okay, so here I want to take another question. Well, let's look at the second aspect of work done, which is work done by gravity or work done against gravity. So one thing you need to note here is that gravitational force, of course, force is a vector, generally speaking, having both magnitude and direction. But the force of gravity always acts vertically downwards. And for an object, the force of gravity is equal to the weight of that object. Recall that weight of a body is defined as the gravitational force that is acting on that body. So the gravitational pull on a body is equal to the weight of the body, and it has a direction which acts vertically downward. So if you must do work against gravity, the object must be moved in a direction that is opposite the direction of gravity, which is downward. It means that if I must work against gravity, I'm going to take an object vertically upward, for instance. So if I raise a body like this pen, I raise it up like this, I am moving against gravity. So work is done by me. So when a body does work, or when gravity does work, we see that the body loses energy, because when gravity does work, the body moves downwards in the direction of gravity. So, but when an external body does work on the body is bound to move upwards. So when I take this pen upward, I am the external agency. I've applied some force to take this pen upwards. See, if I didn't apply that external force, this object will not naturally move upward, because it's under the influence of gravity, which is always pulling it downwards. So when a body, or when a work is done against gravity, it means that the object moves in a direction opposite to the direction of gravity, and then the object gains energy. You see, so the work done or by the external body on that object translates to the gain in the gravitational potential energy of that body, as you can see in this case. So I've been saying a lot about it, but look at my picture here, that the minimum force needed, for instance, to raise this block of mass must be equal to the weight of this body. Of course, you know the weight of a body is the product of the mass of the body and acceleration to gravity. Here I'm taking my G as 10 meters per second squared. That's the approximate value of it on the Earth's surface. So it means that force M must be equal to 5 times 10. If the mass of the body is 10 and G is this, or 5 and G is 10, so that gives me 50 Newton. That's the force. Now the distance moved, I'm going to take this box of mass from this level, let's call that level A, to this level B through a vertical height H. So when I bring this box here, the distance moved is H. The force applied is F. So work done is also force times distance. Force times distance, D. So the force is equal to the weight of the body, that's mg, times the distance, which is h. So the work done is given by the expression mass times acceleration due to gravity times the vertical distance moved, which is the height of the body now above this horizontal surface A. So you can see that work done against gravity translates to the potential energy of this mass. Now look at the second question. A body of mass, an object of mass 10 kg is raised through a vertical distance of 20 meters. Calculate the minimum work done or minimum work required to achieve this. What's the minimum work done? Okay, so here we see that mgh is the expression, is a formula for calculating the minimum work done. So the mass of the body remains 10. I'm going to take 10 as the value of g to simplify my calculation. That is 10 times 10 times 20. That will give me 2000 joule. That's the work done in taking this body of mass 10 kg through a vertical distance of 20 meters. So I'm going to do a total work done of 2000 joule. So, okay, in the next video, I'm going to continue with the aspects of work done. This one I'm looking at work done moving along an inclined plane.